Models. Yesterday, we had an excellent overview of some of the fundamental concepts. Dr. Z is here, so I'll not waste any more time. I'll just hand over to you. So Dr. Phil, it's all yours.
Okay, thank you. Yeah, thanks everyone. Let me share screen first. Okay. Yeah, so hopefully, yesterday's course give everyone a good overview of, the predictive models and the, structure of different machine learning methods and some fundamental ideas, concepts. And I do feel like I might be, going slowly for some of the material, and there's still a lot to cover today. So we will jump into today's material. From yesterday, we introduced, this a linear model, right? We give, some visual interpretation of the beta hat estimate for the linear regression. And these statistical properties for the, low dimensional beta hat estimate should be, straightforward. And I believe most of you should have, learned this in your statistical classes. And now if we move on to large P, right, what we mean by high dimensional data. So that's, a lot of cases in real world applications. So, so in these cases, right, the key question is not only to estimate beta hat, and oftentimes, this beta hat estimate may not be available for all the P, right, because you have a large number of P, but we want to identify a subset of X variables that are most relevant to Y. So that's, one of the goals and the immediate goal we want to achieve when analyzing this high dimensional data. And so another approach that is, different from like this joint modeling of P predictors is that people could do this marginal, could estimate this marginal effects, right? In other words, we could estimate the effect of Y for each single XJ, right, separately. So here for each XJ, people could do this marginal model. And this is what we mean by marginal effects, right? But these marginal effects, they are different from this whole beta hat vector that we would consider for the whole X vector, right? So these are the two separate things, and there are certain limitations if we only look at the marginal effects. So to move on, before we introduce the subset selection or variable selection, we also want to distinguish or formalize this training versus testing error. Right? So we have seen this comparison in the like previous plots when we plot, right, the training error versus testing error. But to formally define the difference is that here you see in blue is our training sample, right, or the outcome yi in the training sample. So the blue yi's, and so they in the training sample, meaning they are observed, right, in our data. And then the red y star, they are independent testing samples, right? So y star is something we do not use for the model, but we want to predict. So because we assume the linear model choose, right? So for both y and y star, we have these two formulas. They are essentially the same, right? So the choose is the same, for both the training y and the testing y. But moving on, when we calculate the training error versus testing error, there is a substantial difference. Okay, so remember, we use the linear regression to estimate our beta hat, right? So this X beta hat part is, what we get from, so this beta hat is what we get from the training data, right? To be specific, this beta hat is what we estimated from the training data dn using xi, yi, right? And then the X is the, X in the testing sample, right? So then with some, simple derivation, right? We minus same, true X beta plus the same, true X beta. We separate, this testing error into two parts. And so the first part, right? The first term becomes so we call this the irreducible error, right? So this y star minus mu corresponding to, this E star in the truth. So the first term is the irreducible, error corresponding to E star. And then the second term, right, is the difference here is, the X is the testing sample X, right? So when we calculate this X times beta hat minus beta, it follows this formula, and it's the trace of this matrix, right? X transpose X times the covariance, or so because beta hat is a vector, right? So this covariance means a covariance matrix, and this trace would be, P times sigma square. So for testing error, we see that it increases, right, with both N and P. So, as your sample size increase, as your, number of parameters increase, your testing error would increase. And on the other hand, right, if we calculate the training error, because, this Y is what we observe in the training data, and then Y hat is the fitted value, right? From the definition of our, beta hat estimate, we see that it would be, the I minus H, the hat matrix, times the error, and with, the same technique, right? It's equals to the trace of this matrix. And the good thing is that actually we have N minus P. So so the degree would, reduce, right, for the training error. So this is, intuitively speaking, as we know, if for the training sample, right, if we have more predictors as P increases, right, we have more explanatory variables to fit the model, then we would reduce the training error, as indicated in this formula. However, on the other hand, actually more complicated model, right, as your P increase, more complicated model would increase the testing error at the same time. So this, explains like the previous pattern that we observe in our plots, and we want to, so that is why it would also become problematic, right? As P becomes larger than N, essentially we have the overfitting problem on the training data, right? So it shows, the one of the challenges or the problem if we use classic method or classic linear regression to fit P greater than N case. Okay. So it is, necessary to select a set of relevant variables, especially when P is large. And with variable selection, it could improve prediction accuracy as well as the interpretability of your model, right? Because, if you have a model of 100 predictors, it is hard to interpret, like the effects of all those 100 predictors, right? If you have only after variable selection, right? If you got only, a final model of 10 predictors, then it may be easier for you to interpret those effects. So there are, some difficulties that are quite, straightforward, and we will, try to encounter those difficulties in the following as well. Okay, so because we want to do model selection, and we need some certain criteria, right, or the objective function that we use to select our important variables. And this is when we come back to this formula that we actually introduced earlier as well. It's just a slightly different form, but essentially, right here, the goodness of fit is what we mean by the loss, right? So goodness of fit, measures how good the model fit your data, right? So smaller loss means, better goodness of fit. So this formula is essentially, the same as the previous loss plus lambda times the penalty, right? And we want a penalty for the complexity of our model, right? The penalty that measures the complexity. So, this is the objective that we come back to. So the interpretation, right, is basically, the first term will decrease as the model gets more complicated. And the second term would increase, right, at the same time. So we want to achieve, the certain balance in order to find the best model. So we start with, some classic model selection criteria. These, you might have used already in low dimensional cases, right? They're not necessary for, high dimensional. AIC and BIC, these, widely used, and the Mallow CP is also like a similar criteria, but, it uses a different loss function or equivalently, right? It's the goodness of fit measure. So for all of these criteria, we see it, has the two components, right? Whether it's the residual sum of square or the log likelihood, they are all, goodness of fit measure. And then we want to penalize, right, for the model complexity. So in linear model, in linear regression, we know, the number of parameters corresponds to your P, right, the number of features. So basically, P is a measure of model complexity here, and we might use different, multiplier in front to that's something distinguish the different criteria. So all of these criteria, they follow the general formula that we proposed, and so there may be some difference in real world application, but the idea behind them are the same, right? So so one remark, regarding AIC versus BIC, right? We see the difference is that BIC have, log n in front of P. So that is saying, so with a reasonable sample size, right? Often you basically have log n greater than 2. So this is saying, we have a larger penalty for the model complexity if we use BIC criteria, right? So so in other words, BIC would choose smaller models. So as what we see here, right? AIC tends to pick a larger model because the penalty on model complexity P is smaller for AIC, right? Another remark, maybe, Mallow CP performs similarly to AIC. So so this model selection techniques is, this paper is a good overview of, some of the classic approaches if you want to, learn more about the on this topic. So the next technique we want to introduce is also, a classic one, right? So-called stepwise regression. And so the idea of stepwise regression is essentially a greedy algorithm, right? So by greedy algorithm, it's a general definition. It means that, we want to optimize at each local step, right? So it's a local optimization algorithm, so that, at each step we want to find the optimal solution to, for example, our goal is variable selection, right? So at each step we want to find the best model selection, but it may not be like the overall, may not be the global optimal solution, right? As we will see a comparison later as well. But it is fast, right? It is easier to implement, and oftentimes it's good enough in practice. So so the stepwise, to be more specific, right? People can do this, either backwards or forward, or consider both, backwards and forward, right? So for backwards, one thing to point out is, because the backward selection, right, start with the full model, and at each step, right, it wants to delete predictors that are least important, right? So essentially here the criteria is that, we delete predictors that are least important at each step. And then this score, right? This score is essentially, what the criteria we saw earlier, right? So for the least important predictors, we see that this deletion, right, or this backward procedure, it is performed locally or sequentially at each step, right? So because it starts with a full model, so backward selection only applies when you have larger sample size than a number of parameters, right? Then on the other hand, we could do forward selection. So we start with the null model. So null model meaning that, it's a the smallest model that, include only the intercept, right? That's the null model. And we would sequentially add predictors, right? So that is, at each step, you find the most important, right? You find the most important predictor at each step. And so this can always be used even for, p greater than n, because we start with a null model. And, naturally, like we would have the stepwise selection that consider both, deleting and adding one predictor at each stage, right? Also here, for these sequential or, greedy algorithms, we would like just change, right? Update the subset of predictors, only one predictor at a time, right? That's the also a key here. So stepwise selection, it's also a classic method. And on the other hand, right, as I mentioned, a more global search, or a global variable selection method is so-called best subset selection, right? So a level-wise search, in other words, it is a global search that we want to find, the global optimal solution for a given model size. And immediately, we will see that because this search is global, right, it's not feasible for P, not P too large, right? And so the idea is that, for a given model size, right, for the given model size K, so K would be from 1 to P, right, smaller than P. we want to check all of the 2 to the power k possible combinations of the variables we have, right? And find the smallest model, the model with smallest criteria, right? Either it's residual sum of square or maybe negative log likelihood, right? So because we see here we check 2 to the power of k, all possible combinations, right? So we know that when k or p is too large, this is not feasible. So so then for each k, we would have a best subset, right? And then the second step is to choose the best k, which goes back to our model selection criteria. We want to penalize the model size k, right? So here k is the model size. So I also want to mention, the R package LEAPS implemented this best subset selection, and that's something you could try out, right? And also, by the way, for stepwise selection, there's a step function in R. We will see the implementation later as well. So one greedy algorithm and then one global search algorithm, right? So let's take a look at a data example, how these methods can be applied. So for this diabetes data, we have 10 baseline variables, right? P equal to 10. It is not a high dimensional case, but for illustration purpose. And we want to disease progression. So there's a Y, right? That is our outcome. So that's the disease progression. Right? So that's the continuous measure that we want to use as our outcome Y, right? And so this data is available, in R package LARS, or you can download from the link. So let's take a look at this data. So for those of you maybe not familiar with R, essentially we start with some essential steps, right, to install the R package that you want to use, and load the R package by calling the library, right, and then load the data by calling the data function. And so because for the diabetes data, the X and the Y are stored separately, right? So we want to combine them, use the column bind function, right? So this is a column bind function. So we combine our Y and X into the same data frame, right? And so there is a data visualization tool. You could either use the pairs function, right, or the more fancier function called chart correlation in this R package, right? You could check out after the class as well. So so they give you the same thing, right, or similar things. Essentially, it shows you the marginal distribution of your data, right? So we see here on the diagonal, panels, we have all of our predictors, right? Age, sex, BMI, so on and so forth, and also including Y, right? So the last panel is our outcome Y. It is a continuous measure, and so we see, for example, for sex, right? It is binary 0 or 1, and all the other measures, they are continuous, right? And it gives the histogram of all the predictors or all the variables. And then on the upper triangle, right? On the upper triangle, these are the pairwise correlation, right? So for example, if we look at the last column, that would be the marginal correlation for each of your predictor with the outcome, right? And they are, scaled with the size or the scale of the correlation, right? So for example, BMI has a larger correlation that is significant with outcome Y, and some correlation may be smaller. And on the lower triangle, right, that is so-called scatter plots. So the scatter plots, right, is essentially you just plot the two variables of your data points, right, and for each of the panels. So this gives you like a good visualization of the data that you have. So let's start with the linear model that we would fit on the whole data set, right? So we would call this LM function, right, that fits the linear regression. So y tilde dot, right? So here the dot means that we would use all of the variables in our data set, right, except for y. So that's just some coding like for short, right? Easier to write. But another way to write this is essentially you write the whole formula, or if you do not want to use all the variables, you would write, for example, y regress on age plus sex, right? So this would be a simpler model, and so we get our LM fit, right? That is the fitted model from linear regression. And if we call the summary function, right, we can output the summary of the fitted model. Here, what we display is only the coefficients estimates, right? So we see here, these are some like very large like beta hat estimates, right? So this first column estimate corresponding to beta hat, and some also have like large standard errors as well, right? And in terms of the significance, right, some are highly significant. So that's the last column, right? P. So this is the p value, the last column. Some are highly significant, some are not. So we suspect, right, not all of the variables here are important in predicting this disease progress measure. So we want to try, some of the selection methods we introduced, right? So so this is when the step function comes into play, right? So you could use the help function or the question mark followed by your function to look at the helper document, right? Essentially regarding the step function, but so when we call the step function, we could specify the direction of our greedy search, right? So the direction is both means we do both the backwards and forward selection, right? And for backwards, that means the first backwards we want to perform. And so the default, right? So the default criteria for stepwise selection or stepwise regression is the AIC criteria, right? So and there are some just additional arguments, right? Trace equal to 0. That means you do not print intermediate results. And so here's the illustration for the forward selection, right? Because for forward selection, we start with the null model, right? Which is let's use a different color, which is this model, right? So this is the null model. We give to the step function, and then so so the scope is, another argument, if you use it, you will learn it. Essentially, it gives the largest possible model, right? So the range of the model that you look at. So from your full model to the null model, right? That's the range or the scope for forward selection. So, that's some coding example for the stepwise selection. And if we print out, so one more example is, when we specify k equal to log n, that corresponds to, the BIC criteria. As we know, the k, right, corresponds to the parameter in front of our penalty p, right? So for AIC, it is 2, and for BIC, it is log n, right? That's the k in our function. So if we use k equal to log n, that's the BIC criteria. So so just for illustration, right? Let's see, if we, so this output is the result from the BIC selection, meaning, the last step function that we use, right? So we see that instead of, all of the 9 predictors, the final model from stepwise would select six variables, right? And the corresponding coefficients as well. So that's, we could perform stepwise selection in R as an example. So in terms of the best subset selection, right, the second approach, we mentioned, we could use leaps. And so the leaps are library, right, after we install it, and the function for best subset selection is this reg subsets, right? Stands for, regression, right? We want to find the best subset for the regression. And so if we run this reg subset to our data, right? So so only thing to pay attention here is essentially, we input our, first is the X matrix argument, right? S matrix, diabetes, data. So this is the X matrix. Second argument is our Y vector, right? The diabetes, the first column for our data, that's the Y outcome. The third argument, NV max, meaning that, at most, right, we have 10. Yeah, sorry, so it's not 9, right? So it's 10 predictors. So that's the maximum number or largest size of the subset. Right? So wait, do I hear someone's not muted? Okay, anyways, so so let's look at, this output and try to understand. So essentially each row of this output, right, corresponding to, the different k here, right? So for k equal to 1, the best subset model is essentially BMI only, right? In other words, we would know that BMI is the most important variable that's associated with the disease progression, right? Our outcome, and so on and so forth, right? For k equal to 2, the best subset is, BMI and LTG. So I do not remember exactly, but I know some of them are like blood pressure measures, like low blood pressure or high blood pressure, and then yeah. So So when you look at the data, you will find the definition of these variables, right? So when you load this data and you look at the data, there are like definitions here, but of the variables. But yeah, I do not remember all their meanings. So for k equal to 2, we would select BMI and LTG, right? And then so on and so forth. So however, there's one more step that is missing here is, we want to choose, right, the best K in this case. So we could choose, the best K using, once again, our either AIC or BIC criteria, right, to choose the best K. So here are, some of the classic approaches, right? Either it's a greedy algorithm or the global, best subset selection. Any questions so far? Yeah, maybe. So yeah, so hopefully, some of you might have used these techniques before, right? And so moving on, we want to introduce the so-called shrinkage methods, the idea, right? So there are, certain limitations of the methods we have just mentioned. For best subset, it's, computationally expensive and it's not feasible, right? When your P is too large. And then for forward and backward selection, there's no guarantee to find the best global submodel, right? It's a local solution. And the selection process is discrete. So in other words, your selection process is not robust, right? So we want to find a continuous process that, does not suffer from the high variability, and more importantly, right, we want the methods to be applicable to the P greater than N cases. So that's when we consider the shrinkage methods. And so to introduce this idea, we start with the error decomposition, right? In other words, this prediction accuracy, in other words, it's just the testing error, right? Or the prediction error that we have introduced. And so this is just like a rewrite of the previous testing error. Remember, we would have this irreducible error, right? In other words, to generate the truth, there would be some measurement error that we do not observe, right? So irreducible error. Then in addition, right, we would have the bias between our fitted model and the true model, right? And the variance of the fitted model as well. So this is a general decomposition for the prediction error or prediction accuracy. So so if we consider this bias variance trade-off, right? The idea is to regularizing, or so here, regularizing, shrinking, or penalization. Penalizing, these three words essentially mean the same thing, right? People use this interchangeably. For these three things, they mean the same idea, that we want to control the model size, right? Or penalize the estimators to reduce the variance, right? Because remember, as we saw earlier, right, as P increases, this prediction accuracy would decrease, right? That's one challenge that we need to overcome. So to overcome this challenge, right, the idea is that we want to control the model size that it does not increase with P, right? So even though you have, large P, but we want small model size. And so, the variance can be reduced. Then not all the good, you cannot expect, all the good things to happen, right? So at the same time, variance decreasing means your bias could potentially increase, right? But, as long as, the trade-off is worth it, right? As long as you have a larger variance deduction and a smaller, bias increase, we would, achieve an overall better prediction accuracy. So that's, the overall goal we want to achieve. Hope it makes sense. So here's one motivating example, that's very simple, but, help us understand the idea, right? So let's say we have this estimated linear model, it is hypothetical, right? With this, arbitrary coefficients that's really small, right? So because this is y hat, right? We know this is a, f hat function that we estimate. So the question is, is this a good model, right? So we propose, we estimate this f hat, for example, from our linear regression, right? So the assumption here is essentially, we would assume this expectation of y hat, right, is the same as the true y, or, we call this the mu, right? Mu is the true expectation. That's, for example, equal to the true x beta, right? So here, beta is the truth, right? The true beta. So this y hat is unbiased, right? In other words. And if we remove, right? If we remove, those x values, x terms with the super small coefficients, essentially, we would have a biased model, right? Because, although they are small, they contribute to the expectation, right? If we remove all these three terms, for example, right, this would be our y tilde, that is only 1 plus x1 to x2. This expectation, does not equal to the truth. It is slightly biased, but, it would also reduce the variance of our prediction, or, of our estimate, right? So that's what we mean by the, bias variance trade-off. And to, quantify this trade-off, right? Essentially, we introduce this model complexity penalty. So this is, the third time we have seen this formula, right? We should be familiar with this criteria. So for this alternative model y tilde, right? Essentially, we would have a reduced model complexity and, slightly increased loss, right? Or the goodness of fit is slightly worsened, but overall, we should achieve a better model. So, we should prefer this model, right? Intuitively speaking, we could see the difference. So, so to, give a so this is, so first of all, right, this goodness of fit plus complexity penalty is a general form that, it's basically a concept, right? So to realize this concept, we formally define, objective function, so-called penalized loss function, right? So in addition to the loss function, we introduce the penalty term, and that's, the formal definition for the shrinkage method. So because we consider linear regressions here, right? So the sum of square residual, right, RSS, can be used as the loss function. It measures the goodness of fit, and we denote the penalty term or the complexity by a function p, right? So p here is a function, and with respect to our beta vector, right, which controls the model complexity. And lambda is so-called tuning parameter, right, which controls the penalization level. So we have mentioned this, if lambda is larger, that means you impose, right, a larger penalty to the model complexity, right? So you would, select smaller models, or you would, prefer smaller models with larger lambda. Okay, and so because this p lambda is, a general function that we could, use like different penalties to, for this p lambda function, right? So, so to write this out, essentially, we will introduce several of them in next, right? So for L2, so people call this L2 penalty the ridge regression. This is because, p lambda of beta is written as lambda times the beta vector L2 norm, right? So, so if this is new to you, let me just finish the writing here first. So for L1 penalty, right, the only difference is that, we would consider the L1 norm, right, for beta, and that's corresponding to the lasso. So, so the L1 and L2 norm, they are just some mathematical definition, because, beta is the vector here, right? And L1 norm simply means, you take the summation of all the entries, right? The absolute value, right? Summation of the absolute value of beta 1 through beta p. And the L2 norm is basically, the summation of this beta squared, right? So each of the beta 1 squared, beta 2 squared, all the way to beta p squared, summation of the squared terms. Okay, so so with this, different L1 versus L2, ridge regression and lasso, they actually perform very differently in terms of model selection, and we will see later as well. And so there are some further extension, right? We may not go into all the details, but essentially, the bridge or elastic net or adaptive lasso, so on and so forth, they are, generalizations or extensions of these two basic L1 and L2 penalties, right? And that's the focus of our material here as well. Maybe for some of you, right, you have heard elastic, and so that is also, widely used, and I think it's worth to point this out. So for elastic net, essentially you have p lambda of beta equal to, the same lambda, right? But it's a combination of L1 and L2. So here is an alpha, right, times the L1 plus 1 minus alpha times the L2. Wait, do we have the squared? Oh, let me double check. Yeah, so it is beta squared, right? Okay, so here, for elastic net, that's the p lambda function, and then alpha is between, 0 and 1, right? So essentially we see alpha equal to 0 corresponding to the ridge regression, right? Alpha equal to 1 corresponding to the lasso penalty. And then, yes? Question? Okay, I guess it's just someone not muted. So let's move on. Right, so so here's a very classic comparison or classic illustration comparing lasso and ridge penalties actually. So so for this illustration, right, we see that we consider two beta values, beta 1 and beta 2, right? So in other words, your beta is only beta 1 and beta 2, and so it's actually a slightly different formulation, but we have the constraint instead of the penalty, but the idea is the same, right? So we see the constraint, right? This square, essentially, yeah, no worries. So we see the square, right? Basically corresponds to the L1 penalty, right? So the blue square corresponds to the L1 norm of beta less than or equal to 1, right? Let's call this the unit square, right? So this dot here is 1, right? And we also know that this circle corresponds to the L2 penalty, right? Beta 1 square plus beta 2 square less than or equal to 1. Right, for this unit circle, it's basically this constraint, right? We know that this function corresponding to the circle here. So and then these contour lines, right? These red contour lines, they are essentially the loss function, right? So the same contour line, meaning we take the beta value with the same loss. So the idea is that given this constraint, right, the blue constraint, we want to find the value that minimize the loss, right? So that would be the intersection here. So when your contour lines intersect with the constraint, then that's our beta 1 hat beta 2 hat selection as beta 1 hat beta 2 hat solution, right? So the major difference here is that we see because of the L1 constraint, right? Then the intersection happens at the corner, right? The corner of the square. So we would have this corner corresponding to beta 1 hat exactly equal to 0, right? And then beta 2 hat would have a non-zero value, right? However, if your constraint is a circle, right? In other words, it's smooth, right? So when it intersects with the contours, it happens at non-zero beta 1 hat and beta 2 hat values, right? So so this is why essentially we would get from lasso or from the L1 penalty, we would get exactly 0 solution for some of the beta, but with ridge or other the L2 penalty, the solution is not exactly 0, right? So this is one illustration we want to introduce. So a little bit more of this same idea, right? So this essentially shows with the different Q, right? So LQ penalty, in general, right? Essentially, we can consider the beta Q, norm, right, as the penalty term. So Q equal to 2 is the ridge, right? We have seen Q equal to 1 is the lasso, and so if for Q that is less than 1, right, they become So we call these two are the non-convex cases, right? So essentially, the solution is harder to achieve, but and then for Q equal to 4, it's basically, the L4 norm, right? So this just, let's see. So in another comparison we want to show is that essentially, the elastic net is similar to the LQ norm when you have Q between 1 and 2, right? So we see that essentially elastic net is something, in between lasso and ridge. And from this, the shape of the constraint, right, we could tell that for elastic net, sometimes it would also achieve, like the sparse selection, right, the contour interaction with the intersection with the contour is, at the corner, right? So yeah, some visual concepts. Now let's move on to the more detailed results. First, regarding the ridge regression, right? So to formally write out this beta hat ridge solution, right? That's our ridge regression estimate, right? We see it has these two components. First is residual sum of square. It is the loss function, and plus lambda times someone. Let me see. I need to mute someone again. Okay. Hopefully it works. So first is loss term, and then it's a penalty term, right? With the L2 norm of beta. It is really goes back to even 1943 when people first have this L2 penalized idea, and once again, right, lambda is called the tuning parameter. So why we call this shrinkage methods, right? As we will see later, this is because the beta hat values are shrunk towards 0. Okay, so essentially you have smaller beta hat values in absolute value, right? And so actually this equivalent formulation, right, that's equivalent to our argmin formula, is that we can write this as a constraint, right? So subject to this L2 norm less than or equal to a constant S, right? This constraint is exactly what we saw in the previous plots, right? So these two formulations are equivalent, and in practice, I think this is important, right? So ridge regression is especially useful when we have highly correlated covariates. That's something you want to keep in mind when you apply ridge, right? So when do you want to apply ridge, right? If you have correlated covariates, ridge can help mitigate this high correlation. And ridge regression, right, elevate this problem by imposing this size constraint. In other words, penalize the beta estimates. And yeah, let's look at this illustration to give you an idea. So here we plot this basically so-called the ridge constraint solution, right? So the x-axis essentially corresponding to like the degrees of freedom of your model, but in other words, towards right, corresponding to lambda equal to 0, and towards left, corresponding to larger lambda, right, as lambda increases. So why is this, right? So let's say we have all the predictors, or all the predictors, right, indicated by their names here. So without penalty, right, lambda equal to 0. So this so we can think of this plot as, like the different columns, right? So the last column essentially is, the beta hat estimates, right? With lambda equal to 0, they are, unpenalized. They are from your original linear regression, right? Then as your lambda increases, right? So as your lambda increases from right to left, so this is, lambda increases, we see the shrinkage effects, right? So beta hat becomes smaller and smaller, the shrinkage effects. And all the way, right? If your lambda is large enough, for example, lambda is towards infinity, right? For lambda large enough, all of our beta hat ridge, right, would go all the way to 0. So at the end, your beta hat ridge becomes 0 for lambda large enough. And so the idea is that, basically want to choose an appropriate lambda, right, or the best lambda that gives us, some shrinkage, that's, like a optimal model in some sense, right? So this is, yeah, let's, look at one implementation here. So let's see. So this is, one illustration when we have correlated variables, right? And then we want to apply ridge. So here we simply, simulate two predictors, right? X1 and X2. We see here X1 and X2 following multivariate normal distribution, and they are highly correlated, right? So the correlation between X1 and X2 is, 0.999, right? Because, this matrix is the covariance matrix, right, that we specify. So 0.999, like this, right? So X1 and X2 are highly correlated. And then we simulate Y, right, following, this mean of Y equal to 1 plus X1 plus X2 plus the random error, right, epsilon. So if we directly fit this linear regression, right, we see that the values of, the beta hat, right, they are very large. So it's essentially unstable, right, with a high variation because X1 and X2 are highly correlated. However, if, and we see, these beta hats, they are far away from the truth, right, because this is a simulation. We know the truth, right, the true beta 1, beta 2 equal to 1, right? And if we apply, LM.ridge, right, that's the, ridge regression, we can fit. And we pick, a suitable lambda value, lambda equal to 5. And this is the coefficients we get, right? So we get beta 1 hat ridge, right, equal to, this 0.87, and the beta 2 hat ridge is this 0.98 value, right? They are much closer to the truth. At the same time, we see, they are shrunk towards 0, right? Meaning that their absolute value is, smaller than the truth, right? So they are, shrunk towards 0. That's exactly, what's like this kind of effect shows on this plot, right? As you have a penalty term with lambda, your beta hat estimates, they shrunk towards 0. So here's some more mathematical derivation. I think we could briefly go over them. Essentially, how we can write out the beta hat solution, beta hat ridge. And something to highlight here, right? As lambda goes to 0, beta hat ridge is, the same as the ordinary least square. And then as lambda goes to infinity, beta hat ridge goes to 0, right? Then, yeah, so there's like a remark on the scale of predictors, right? Because, we apply this penalization term. So in practice, right, it is always recommended to normalize, your predictors or standardize, right? Standardize your predictors before we fit the penalized regression. It's, for like a more stable solution. So that's something to keep in mind, right? To normalize the columns. Some more derivation. I don't think we need to go over this, but we can, if we just look at the conclusion here, right? So the idea is that, beta hat ridge does have a bias term, right? So it is not unbiased, and it achieves, right, the variance reduction as we see here, right? So the variance of beta hat ridge, it is smaller than the variance of beta hat OLS, and it's controlled by lambda, right? So for larger lambda, we see that, this multiplier, right, becomes smaller. So larger lambda means, smaller variance, but larger bias, right? That's the conclusion here. Okay. Some more, theoretical derivation. We would skip this. So here's, some summary, right? But yeah, this is just some further, interpretation. I think this is fine. Degrees of freedom, right? So remember, for degrees of freedom, it measures our model size or, the complexity of the model, right? So remember, when your degrees of freedom is larger, that means, it's a larger model, right? And for ridge regression, we could derive that essentially, for ridge, right? For ridge regression, so first of all, the degrees of freedom should be between 0 and p, right? Because, at most, you would have p parameters, right? And for the least model, all of your beta are 0, right? So that degree of freedom is 0. And yeah, so we will derive it later. But so the basic idea is, as lambda increases, right, your degree of freedom decreases. That's the basic idea, right? You would have smaller models. Then, with some derivation, let's see. Yeah, so this formula, you do not need to memorize this, but essentially it shows you that, for lambda equal to 0, right, you get degree of freedom equal to p. And then for lambda becomes larger, you get smaller and smaller degrees of freedom for ridge, right? Okay, so that's the takeaway for degree of freedom. And so this is an example we have seen. And one last, unsolved problem, right, is that we need to choose lambda. So, for example, given this solution, right, this is, the plot of solutions with respect to, different lambda values, right? So any vertical bar here corresponds to a ridge selection, a ridge solution with different lambda value, right? And how do we, determine the best lambda that we should use? So to choose the tuning parameter, we basically, you know, we could use the cross-validation idea, right? Because so the fundamental idea is that, you know, you want to use an unbiased prediction error, right, to choose your best model. So that's when cross-validation comes into play, because, you know, through cross-validation, we could estimate the prediction error. So, so specifically, right, there's a technique called the leave one out cross-validation, meaning that, you know, instead of the k-fold cross-validation, right? So previously we mentioned the k-fold cross-validation, but essentially here is that, you know, we want to hold out each sample, right, the RS sample at one time, and fit our, you know, ridge regression based on the remaining n-1 observations. And we want to predict, right, or calculate the prediction error on the holdout sample. So that's the idea of, you know, leave one out cross-validation. And repeat this, you know, for every single sample, right? We get the cross-validation error, the CV here, right? So each one of these beta hat minus I, right? It is, you know, estimated using n-1 observations, right? So this leave one out cross-validation, you know, is an unbiased way to calculate the error, and essentially we only need to, you know, minimize this CV, right? So if we write this out, you know, our optimal lambda, right, is essentially the arg mean of all the lambda values, right? That's, you know, look at this CV, right? So implicitly, you know, this CV depends on the different lambda value, right? So for different lambda value, you get different the leave one out cross-validation error. And we just want to, you know, pick the lambda hat that minimize this cross-validation error. So here's just some, you know, more derivation. And basically, right, so as we wrote earlier, you know, this cross-validation depends on your lambda. And basically, you want to, you know, choose the lambda that minimize this cross-validation error. So there's also a modified version called, you know, generalized CV, but the idea is the same, right? So you either minimize this CV lambda or, you know, minimize GCV in order to pick the optimal lambda. Okay, yeah, so all of these, you know, they are also implemented in R packages. So you do not need to, you know, calculate this by yourself. And we will see, you know, some of the implementations later. That we will see more implementations later as well, okay? So that's, you know, pretty much what we introduced about ridge regression, right? The key here is that, you know, for ridge, right, our penalty term is the L2 norm of beta, right? That's something to keep in mind.
In fact, yeah, I just joined the RCMI training. He organizes RCMI data science training, and I've just joined it.
Are you talking to me? I think there's a raised hand. Yeah.
Yes. I was going to bring that up. So yeah, sorry for that. So a question I have though, this is really a great material. I think it's really I'm learning. I mean, I'm a lot of questions I had on my head have been basically addressed. But one thing that keeps bothering me is, and I'm sure it may also bother some students. For the most part, when these shrinkage and penalization comes in as far as ridge and the lasso, it becomes a little bit of an abstract, right? It becomes a little bit of, unless you've seen this in a real environment, which I have seen it multiple times. You don't appreciate it much. I mean, later on, I think you appreciate it, but you don't appreciate it much. Now, if there were like real examples, because primarily what you have here is that you're trying to compute an inverse of the matrix X, which are the features, but then the matrix is not invertible. So matrix is not invertible, you can't get an inverse, therefore you can't compute beta. Right. So, and then that's primarily what it is. Yeah, so when you are faced with that situations, this is one of the ways you can do it. One other way you could also do it, which I don't think people do, is why don't you just estimate? I mean, fill the matrix up with, I mean, we have a lot of, assume they are missing values, and you can use comma filtering, you can use all sorts of estimation algorithms to stick them in there. And then you could use PCA or some algorithm to determine the variables or the features that are important, right? And then go with it. Yeah. So I'm sure there's a reason why people have gone through this, because it works. But why don't we look at the other aspect where you can fill out the matrix, get your index, and then go with it? I mean, what is it because of the computational complexity, or is it? I mean, is it? Yeah. So I think that's the only thing that
I see. So make sure, you know, I understand your question. I think you are saying, you know, in the classic case, right, we could invert this X transpose X matrix, right, to get, you know, our beta hat estimate when P is small, right? And then when P is large, we cannot do this inverse, right? And that is, you know, this ridge and the lasso, they come into play, they help with the problem. And this is really a very good question, you know, and actually people, and your question is like, why don't we directly estimate this inverse, right? Even for P is large, right? This is a very good question, you know, because actually the best statisticians, they try to do this problem several years ago, and that actually leads to, you know, like a different research topic. And, you know, people do try to calculate this inverse directly, even when P is large. So obviously, right? So the difficulty here is that your X transpose X is basically a P by P matrix, right? So, you know, P is large, the matrix is large, so it's harder for you to, so you can only approximate this inverse, but you cannot get a, you know, exact solution. And, but, you know, people do this, and it's just, you know, it's essentially like a different approach from the penalization. So, you know, we call this shrinkage methods, right? And if we estimate this P by P matrix, it's actually falls under the high dimensional inference topic that we will discuss later as well. So yeah, it's a very good insight you have, you know. I don't know if you have seen this before, but you know, if you think of this like on your own, it's, you know, very, you know, innovative thinking. I think you try to like estimate this P by P matrix directly, right?
Yes. And also considering that now we have high performance computing, I mean, now we do have computer power, right? So we shouldn't let classical, limitations of classical statistic hold us down. You know, that's what I think. Yeah, this is machine learning.
Exactly.
We have the tools, we have the resources. We shouldn't let mathematicians hold us down. Statisticians, not that I have anything against them, but I think we have the tools, and we should be able to get a way around this.
Yeah, exactly. So, you know, to like estimate this P by P inverse, right? And also, by the way, this inverse is called the precision matrix, right? You know, we do have a name for precision. Wait, I think I spelled it wrong. anyways, so this is called the precision matrix. And, you know, it is more computationally, harder, right? Computationally, it's harder to, estimate, but people, do develop methods in order to, directly estimate this. Yeah, thanks for the question. Okay, yeah, so for now, we will finish the shrinkage methods first, and probably we will talk about, more of these advanced techniques later as well. So yeah, actually, I think it's good to, take a 10-minute break, and then we will move on to lasso. We'll come back at 9:35. Okay. Hello, everyone. I'm back. So, yeah, I feel like, I do have a lot of materials left we try to cover. And there's, one more lecture notes. So we'll maybe try to go over some of the materials faster. And so let's, continue with the lasso first, right? So mainly, the idea behind the lasso is that as we see for comparison, from this ridge regression, although the ridge estimates, right, they are shrunk to 0, meaning that, we control the model size, but the solutions, they are not exactly 0, right? Except, if we go all the way so that, all the beta estimates are shrunk to 0, right? So, however, we want to, achieve something called sparsity, right? The parsimonious of our model. So this means that we only, want to select a small subset of predictors, meaning that, for some of the beta j's, right, we would have beta j hat not equal to 0. But for the rest of the j, right, we want our beta j hat to be exactly equal to 0. So that means what we mean by the sparsity, right, of the model selection. So as we seen, in the previous, like the constraint solution plot, lasso is potentially able to achieve this goal, right? So the so first of all, right, the lasso solution can be written as the objective of this function, right? Instead of the L2 norm, we see that lasso imposes an L1 norm, and lasso, by the way, stands for least absolute shrinkage and selection operator, right? So the absolute here refers to the L1 norm. It's taking the absolute value of all the beta j's, right? And the key property for lasso is that it achieves selection by enforcing some of the beta j's to be exactly 0, right? And so same as ridge, we have the equivalent formula where the constraint is on the L1 norm, right? So So here's also, a visualization of lasso penalty versus ridge penalty. So we see, instead of like a ridge, which is a smooth red curve, right? Lasso has, a sharp bond, right? So that this contributes to, the selection effect of lasso. Once again, this is the constraint plot that we've seen earlier. So there's some, mathematical derivation, which essentially shows us, why or how lasso achieves exactly zero estimation. But, we could just go to the conclusion here, right? So let's come to this conclusion, equation 1 here. So this is, looking at a single beta hat J, right? For a single J lasso solution. And the key here is that, we see if the beta hat OLS stands for the least square, right? Ordinary least square. If the beta hat OLS is small enough, right? So the absolute value is, less than or equal to this lambda over 2, where lambda is our lasso tuning parameter, then we would get the beta hat lasso to be exactly 0. So here is, where the exact 0 solution comes from, right? And for, beta hat J OLS that is larger, right? In the, in the other cases, we see that the beta hat J lasso is essentially a shrinkage, right? It's shrunk towards 0, but it's not exactly 0. So this is how the lasso could distinguish between exactly the 0 solution versus a non-zero solution. But also one thing to point out, right? This is an illustration example under orthogonal design, meaning that all of our x variables, they are independent, right? Orthogonal design, they are not correlated. A simple case, but for illustration. So the conclusion here is that with like a certain lambda value, right? We would have some of the coefficients to be shrunk to exactly 0, right? Which achieves variable selection. So that's the lasso solution. And in terms of the computation, we could get some similar the solution path as the ridge, and also the here is that the point here is that lasso does achieve unique solution. Here unique means for each lambda, right? So given lambda, lasso would have a unique solution under certain regularity assumptions. But yeah, we will not go into too much detail. But there are several different algorithms in terms of the computation of lasso solution. Yeah, if you are interested, there's more reading material. But yeah, so that's optional, right? You could go into more details for these computational algorithms. Some are faster, right? I believe currently the most widely adapted is the coordinate descent algorithm. It is implemented in the GlimNet R package, right? So the GlimNet R package is the major, mostly used package for solving penalized regression or like all these shrinkage methods, and it is computationally faster. Okay, so here's the illustration of lasso solution path, right? So the key here is so each line here, right, corresponding to one predictor, X. So indicated, here, right? So this one essentially is the, solution path for X1, right? So this first line. And the X-axis, right, once again, shows us the sparsity of the model. So towards right, essentially we have lambda equal to 0, meaning, all the betas, right, they are estimated as non-zero, right? So that corresponding to beta hat OLS with lambda equal to 0, right? And then as we, go to the left with larger lambda, right? Then, all of the beta hat, right, becomes 0. All of the beta hat lasso becomes 0 for your lambda that is large enough, right? So the major difference we see that, compared to the ridge solution, clearly, right, the lasso estimates, they goes to 0 at different, lambda values, right? So, so which means, given certain lambda value, right? Let's illustrate here. So given certain lambda value, right? For like this lambda value, these two beta, they become 0, right? They are already 0 for this lasso solution, but the other, beta values, they would be non-zero. So that's when lasso achieves variable selection, right? In other words, it would only select those beta hat with non-zero estimates, right? And another example is, if we look at this lambda value, right, then there would be only 3 beta that's, selected, because, these 3 are non-zero, but all the other beta values are exactly 0. So, we want everyone to see the difference, right, between the lasso solution and the ridge solution, where lasso, achieves 0 estimates, right? And in terms of, lasso degree of freedom, it's actually quite straightforward. So, the degree of freedom for the lasso solution approximately equals to the number of non-zero estimates, right? So this is like the number of non-zero estimates. So this is, also intuitively speaking, right? So essentially, as your lambda equal to 0, the degree of freedom is just the p, right? The total number. But as your lambda increases, some beta becomes 0, and your degree of freedom would reduce, right? Decrease. And so, for example, for this lambda value, lambda 1, right, the degree of freedom is approximately 3, corresponding to the 3 non-zero betas. Okay, so more generally, right, we can briefly go over. So we want to be aware, there are other penalty terms with LQ norm, and we have seen this elastic net formula, right, which is a combination of L1 and L2. And let's go over some implementations. Some of these we haven't touched, but I think the most important one, right, we want to highlight is the GlimNet R package. It's really widely used, and also this cv.glimnet function, it automatically performs cross-validation, whether you want to fit ridge or lasso or elastic net. It performs cross-validation for you to choose, right, to choose the optimal lambda. So that's a very important function to keep in mind. So let's look at the GleamNet example, right? If we install the package and then let's simulate some X values, right? So once again here, X1, X2 are highly correlated. And X3 is independent of them, right? And then from this formula, we see that essentially we simulate Y to be, a linear combination plus the error term, right? So if we simply fit, the GleamNet function, right, the default is the L1 penalty. So meaning that we fit a lasso solution. And if we specify alpha equal to 0.5, that's the elastic net solution, right? Because remember the formula we wrote earlier is, we have alpha times beta L1 norm plus 1 minus alpha times beta L2 norm, right? So alpha equal to 0.5, meaning it's the combination of L1 and L2 norms. So let's see. So this is, the lasso solution, right? So because, it's essentially this lasso fit, right, that we plot here. It would, as lambda increases, right, essentially, the estimates would go to 0, but at a different pace, right? So the problem here is that, actually because L1 and X1 and X2, they are highly correlated, right? So for lasso, it's actually, cannot distinguish X1 and X2. So we see here we may not have like a very good or close to choose estimate from the lasso solution for any of the lambda values here, right? So that's when this elastic net becomes useful, because remember the ridge penalty, right? It helps with the highly correlated case, so that so we could tell from here is actually this black and red curves, they should corresponding to the coefficients for X1 and X2, right? In other words, they are the beta 1 hat and beta 2 hat, right? And then this green curve should corresponding to beta 3 hat. So we see that after adding the ridge penalty, right, we get more accurate coefficient estimates when we have this highly correlated X1, X2 case. So so that's one potential issue, right, we want to keep in mind for the lasso, is that when you have highly correlated covariates, using only the lasso penalty may not give you the good solution, right? But you may want to consider the elastic net that accounts for this kind of correlation. Then you should have a better solution. So we have seen some of the shrinkage methods, specifically lasso and the ridge for as examples, right? So yeah, so I think the reminder is quite theoretical. It's essentially people have been developing this so-called oracle property, right, for the shrinkage methods. Maybe one thing to point out is like we consider this we call this like the active set, right? Or essentially it's the true set of the variables that's a non-zero, right? So the so-called oracle property is that, you know, we want to consistently estimate this active set, which is, you know, much smaller, right? It's much smaller than the total number of predictors we have. And so essentially, you know, why our outcome, right, only depends on this smaller subset of S, right? So we want to estimate this active set and, you know, estimate their beta effects. That's so-called oracle property. So it's quite, you know, theoretical, and I do not think we need to go over this. But essentially, these are the things, you know, people want to achieve. Let's see, biased estimation. So one more topic, right? Maybe we briefly go over a so-called bias correction, because, you know, so what we have learned, you know, for both lasso and ridge, right, the L1 and L2 penalties, our beta hat is actually a shrinkage, right? Shrinkage methods. So it's in absolute value, right? It's smaller than the truth in absolute value. That's what we mean by shrinkage, right? In other words, it is biased, right? For, you know, both lasso and ridge. And, you know, this bias estimate is not desired in practice. So people try to, you know, come up with ideas to fix this or, you know, to do this so-called bias correction. And there are several, you know, methods. Non-negative Garrett is, you know, a modification to the estimation procedure. Adaptive lasso is, you know, so it's like you try to fit lasso twice, right? By giving, you know, like weights to your lasso penalty, you try to get unbiased estimates. And for these two penalty terms, right, they are essentially, you know, we change the p lambda of beta function, you know, to define a specific p lambda function, then in order to achieve, you know, this unbiased penalty, unbiased estimate property. So without, you know, going to too much detail, we can just look at some illustration of the performance. Yeah, something. Maybe not this one. Yeah, so let's look at the estimates. Maybe, you know, like the first is like this one here, right? So here, essentially what we show is, you know, comparing this beta hat, right? Let's see. So on the left, right, we have the lasso, and on the right, we have this so-called non-negative Garrett shrinkage. And we plotting, you know, this beta hat versus beta tilde, right? So essentially, beta tilde is what we get from lasso. Beta hat is, you know, you can consider this as a truth, right? So for lasso, we do see, you know, it is a shrinkage. So beta tilde is less than beta hat in absolute value. And sorry, I think it's the other way around, right? So beta hat is less than beta tilde in absolute value. So beta hat is let's write it here, right? Beta hat is the lasso solution. Beta tilde is the truth, right? So, and even, you know, we see that for small beta tilde, right, we get the lasso solution as exactly 0, as we circle here, right? So that's the lasso, you know, shrunk to exactly 0, and it is biased, right? Indicated by, you know, the difference. So like this is the difference, right, between beta hat and beta tilde. It is biased. But the idea of non-negative Garrett is that, you know, when the truth is small, right, the estimate is still exactly 0. So, you know, it achieves the variable selection. But as your truth becomes larger, right, we see that the bias also becomes smaller. So that's the idea behind it, right? So we want, the estimate to be closer to the truth as you have, larger effects. So that's the comparison, right? So in other words, it becomes unbiased as your beta CUDA, the truth, right, becomes larger. So for adaptive lasso, actually, maybe just one thing to point out, right? We see here, instead of, lambda times the L1 penalty, we see that it gives different weights, right? Different weights that is proportional to your effect size, right? To the true beta. So this is also, essentially for larger beta CUDA, that is the truth, we have a smaller penalty. So the bias would also be smaller, the same idea. So in terms of the, unbiased penalties, right? So we do not need to go into the technical details, but essentially this is, the penalty function that's specified by the SCAD penalty, right? So this is a SCAD penalty, and essentially the idea is for the SCAD penalty is in blue, right? So once again, for larger true beta value, right? We see the x-axis is beta. So for larger true beta value, you do not increase your penalty, right? If your penalty becomes a constant, so that means you penalize those large beta smaller, right? So that you would get, less biased estimates for those large beta. So what we observe here, right? Similarly as before, for lasso on the left, right, there is a bias term, even as the true beta is increasing. But for the SCAD, right, so this on the right, right, it's the SCAD beta hat estimate. We see that, as the true beta increases, actually this bias becomes 0, right? So as the true beta increases, the bias becomes smaller and smaller. And for true beta, large enough, it would be unbiased, right? So at the end, it is unbiased. So similar, the similar thing with the MCP penalty. It's just, slightly different mathematical formula, but the idea is the same, right? You want, you want the penalty to remain to be a constant as your true beta increases, right? And it achieves, similar performance. So yeah, I know we didn't go into too much details, but some of them are quite technical. So we will, want to mainly introduce the idea. And okay, so I think we will stop here for this, lecture notes. Any questions before we move on to the next lecture? Okay, so yeah, so let's, take a pause on this shrinkage methods, right? We will further introduce, some of the other techniques that's useful. And so this is the overview of, this chapter. So basically, we want to introduce or, give some more details on some of the resampling methods, right? Cross-validation, bootstrap, and how we can use, the resampling techniques for model inference and model averaging. And at the end, you know, I think if we have time, we will also introduce a more recent development in, you know, high dimensional inference. And actually that's, I believe, what the question from William, right? When people try to, you know, in the P greater than N case, right? How can we make inference on, you know, beta hat, right? In other words, you know, that is you like we want to give, you know, unbiased estimates for beta hat, right? So E beta hat equal to the truth. So for example, the truth is denoted by beta 0, right? The truth, and then we want to, you know, give asymptotics, right? The variance of beta hat as well. But we will, you know, talk more details later. So to start with, you know, let's also review, right, our error terms that we have defined, right? So previously, you know, we talked about the training error versus testing error, right? So the training error is, you know, essentially the average that we take on our training samples, right? So this formula should be familiar to everyone. And then, in other words, you know, the testing error, we can further specify it as, you know, the testing error conditional on a certain testing set, or, you know, the expected testing error, meaning that, you know, it's not given like any testing set, right? So here, the T, this T, right, means the test set, you know, that is different from our training set, right? So this should be, you know, some concepts that we, so we, you know, we at least, right, we want to know the concepts, but the exact mathematical forms, you know, formulas, you do not need to like derive them by yourself, right? So here's the illustration of, you know, training error versus testing error. Actually, we have seen something similar before as well, right? So so basically here, you know, the blue ones corresponding to the training, right? So we know that as the model complexity increases, right, the training error is always decreasing. And the red curves, right, corresponding to the testing errors. And so each of the, you know, each of the single curves, right, they essentially corresponding to individual samples, right? So the light, right? So the light, let's say the light red curves, right? They are essentially, you know, for each individual test samples, right? And then by taking the average, or, you know, taking the expectation, we get this second one, right? The expected test error. That is, you know, the average. So, you know, this is more of like a review of what we have mentioned. So, generally speaking, right? So, or this is like the most rigorous way, you know, we want to specify the so-called model assessment procedure, right? So rigorously, you know, to do this, right, to do model assessment, essentially we want 3 parts of our data. So they are, you know, the training, validation, and the testing part, right? So use the training part of the data, right? Essentially we fit our model, and, you know, we fit the models, right? So the key point here is that, you know, we could have many models, right, that we want to fit, M1, M2, you know, all the way to MK. That's like a set of candidate models, right, we could fit on the training data. And then independently, right, or separately on the validation portion of your data, you essentially evaluate, right, evaluate all these different models, M1 through MK, to get, you know, so-called prediction error that is unbiased, right, that you evaluate on your validation data set. So, so in other words, you know, you basically derive this error for your model MK, right? And you want to minimize, right? Yeah, that's so essentially, you know, it's like the arg mean, right, over your index of models. So you evaluated this prediction error of all your models, and you select the best model with the minimum, you know, prediction error. So that's the purpose of the validation set, right? So with the training and the validation, you get your best model. Let's say from the training and validation, you get your best model M. We call this, you know, M best, right? So M best is your final model, and you basically, you know, could use, right, or apply your best model in any of the future data, or, you know, the test data that is also you know, independent from your training and validation. So your test data is some external or future data set, right, that you could apply your final model to it, right? So this is the, you know, regular, so that's essentially people with rigorous statistical training, right? We want to carry out this kind of procedure in order for us to reach unbiased, you know, analysis, right? So in reality, you know, mostly, you know, I think 99% of the times, right, we simply focus on this training and validation step. Essentially, you know, with our data, right, I think it is kind of, you know, like good enough, right? Even not all the times, right, people perform this training and validation with our, you know, data set to derive like you know, best model or find the best model. And we may not have the luxury, right, to, you know, have this additional testing data. But the point is, you know, at least you should keep in mind of this training versus validation, distinguish these two, right? So that your derived model is valid. So you know, given this procedure, essentially the k-fold cross-validation is essentially, you know, saying, given a single data set, right? So for this single data set, we perform the k-fold cross-validation to, you know, achieve the first two steps, right? To achieve the training and the validation steps, right? Using this single data set. Yeah, we have seen this, you know, multiple times, right? So this should be straightforward to you, you know, because for each fold, right, we separate the training and the validation. So it is, you know, a unbiased way of estimating the error, and we iterate, you know, between all the folds. So we use a single data set to achieve this training and validation step, right? So based on k-fold cross-validation, essentially, we could choose, right, or, you know, optimize any given tuning parameter. So here the tuning parameter alpha essentially, you know, corresponds to the different models, right? The different models that we consider. So with the cross-validation error, you know, corresponding to the different tuning parameters, essentially we want to have alpha hat, right, the best tuning parameter that minimize this cross-validation error, right? We want to minimize the cross-validation error with respect to the alpha value. So at the end, you get your alpha hat. Essentially, you get your best model, right, corresponding to alpha hat. So specifically, in real data application, typically we would choose k equal to 5 or 10. And if you do have a very large n, right? If you have a large n, you might choose k equal to 20. But I think at most, people would do k equal to 20. And there's a special case we have seen earlier as well, right? The leave one out cross validation, meaning that it's essentially k equal to n, right? So here's another illustration of how to choose k, right? Whether you prefer k equal to 5 or 10. And the short answer is the choice of k depends on your sample size. Right? It depends on your sample size n. So so the idea is that you want sufficiently large sample as your training set, right? So if your n is smaller, essentially you should choose a smaller k, and if your n is larger, you have the luxury to choose larger k. And another thing with picking the final model, right? There's a so-called one standard error rule. I think it's also very important in real-world applications, because we emphasize on the idea of parsimonious, right? So the idea is that we want to come back to this CVF hat alpha function, right? So you might have the alpha hat that minimize this cross-validation error, right? But in practice, you may have some models that's very similar in performance, right? Similar by their performance differ within one standard error, right? So whose the cross-validation error is no more than one standard error within the best model, right? So in those cases, when we compare these similar models, we should choose the most parsimonious model, right? So that's essentially a preference on the parsimonious of your model, right? So as illustrated in this plot, is basically, let's see. So the prediction error is the orange, right? The cross-validation curve is the blue curve, right? So let's focus on, let's see. Let's focus on the blue curve first, right? So misclassification error. So we want to minimize this error, and the absolute, so the smallest, right? The smallest error occurs at this sample size or the subset size p. In other words, it's the model size, right? So for model size that is 10, we achieve the absolutely the smallest error. However, right, we would value the model parsimonious. So that means if we look at the smaller model, right, that is within one standard error, indicated by the bar here, right, then we would prefer the model to its left, right? So the model to its left, it achieves very similar misclassification error, and within the same bar, right? But it is a smaller model, So essentially, you know, we should pick the model size of 9 instead of 10. So that's the idea, you know, for the one standard error rule, right? Yeah, so it's, you know, something to always keep in mind that, you know, we would prefer simpler models, right? If they are similar, you know, in performance. Okay. So another thing to point out is that, you know, in practice, it's oftentimes, so hopefully, you know, I think in recent years, I think statisticians are more, you know, vocal about, you know, the right way to do model selection and the right way to do cross-validation. So people should have less of this misunderstanding, right? But, you know, I think it's worth to, you know, point out to everyone once again. So the idea is that, you know, oftentimes, right, we want to do some sort of screening if we have, you know, a larger number of predictors. But if you perform, right, so the wrong way, right, the wrong way to do cross-validation here refers to, you know, if you perform the screening before cross-validation, right? So, you know, the idea, so the misunderstanding is that we use, you know, the whole data set, right, to select a subset of, you know, good predictors. That's essentially the, you know, screening step, right? You could either use, you know, linear or marginal model, right, univariate correlation to do this screening. And after screening, right, you use just this subset to, you know, perform cross-validation, right? So it may be, you know, a multivariate model, or, you know, like a penalized regression or any shrinkage methods you apply, right? But if you do the screening before cross-validation, that's essentially, you know, you are, so I think people call this something like you, you know, dip into the water twice or something like that, right? So you dip into your data twice, right? So you use your same data set first for screening and then for cross-validation. So you use the information twice, and essentially the result is, you know, biased. In other words, when you estimate, you know, like the effects of your predictors, right, you would get biased effect estimates. So for compare, right, so the idea is that, you know, leaving samples out after the variables have been selected, or, you know, after the screening, right? So violates the independent test set assumption. In other words, you know, your validation step is not independent. So let's, you know, clarify on the right way to do cross-validation, right? So it is also, you know, simple that you try to keep in mind. It's basically the cross-validation, or, you know, the k-fold data split should always happen, you know, as the first step, right? So you always, you know, perform this random split of your data, you know, into k-folds before any of the screening or model selection happens. So this is your first step. And then for each of the fold, right, you could find a subset of good predictors, or, you know, any of the screening techniques, right, you can apply, but to, you know, apply to the k-1 folds, right? So the k-1 folds is your training portion of the data. Oh, so I also see a question actually earlier. So is there an ideal size ratio for training and validation, right? Yeah, that's a good question. You know, yeah, there is some empirical suggestion, right? So essentially, people oftentimes, right, if you have large enough sample size, oftentimes we would suggest like 8:2 ratio. 8:2 ratio for your training versus validation. And if you want to do training validation testing, right, sometimes people suggest 8:1:1 ratio. So you like left out 1/10 of your data as pure testing, right, at the end. So sometimes you may not have like a large sample size. So to ensure the model has enough training samples, you could do like 9:1 ratio for training versus validation. That's also like a convention. Okay. So let's continue here, right? So the key, to keep in mind is basically you want to do the k-fold split before any of the screening or model selection took place, right? So after screen, so within, for each fold, right? Within this each fold, you can perform screening and then build this multivariate model, right? And essentially at the end of step 2B, right? At the end of step 2B, you get your model MK, right? And then you use model MK to, predict the class labels for the samples in fold K. In other words, it's the cross-validation step, right? You calculate the cross-validation error, using your model MK. So this way, right? So essentially, you keep your screening after the k-fold split, and that's the right way to do it. Okay. So, so I do not want to confuse you, but there's one more remark regarding cross-validation. Is essentially so I just say it very briefly. If your initial screening is unsupervised, right, meaning that it does not use the Y information, then it could happen before the k-fold random split. So that's the only exception here, right? Yeah. So just briefly, okay. So the next topic is the so-called bootstrapping, and it is really a very important statistical tool that people use a lot, right? So also I believe so. There's a quote I want to mention to you. Once there was a wise man, or some, I believe it's like one of the famous statisticians that mentioned, there are really only like 3 novel, statistical tools that can be used, for any sort of data analysis. There are, 3 novel technique tools, and one is so-called permutation. In other words, let's call this the data manipulation, right? For data manipulation, helps you get the most of your data, out of your data, and they are, the scientifically sound ways, right, for you to do this analysis. One is permutation, meaning that, if you permutate, right, your X variables, you would, destroy the association between your X and Y. So essentially you could develop some sort of like null association, right? You get your knowledge of the null model in some sense, right? And a related idea is so-called empirical null, empirical null for people, you know, to evaluate this, generate null data, right, from your existing data. And the second technique is essentially, you know, the bootstrap or the subsampling. Yeah. So we could call this the resampling idea, right? So by resampling, what we essentially achieve is that, you know, we create more data samples than we have, right? So we are only given, you know, the sample size 1 through n, but through the resampling, we could, you know, mimic, right, the data we have, and in order for us to, you know, derive more statistical properties from the data we have, right? So, and then the third one, yeah, actually, I kind of, yeah, I do not want to, you know, give you some false information, but yeah, I need to think of the, what's the third one? Yeah, anyways, so the point is that, you know, resampling is a, you know, very fundamental and useful technique for data manipulation. Or maybe the third one is actually just, you know, the cross-validation, but I need to double check. Yeah, maybe it's cross-validation. Yeah, I need to refresh my memory. But so the point is that, you know, resampling or, you know, bootstrap resampling is a fundamental technique that's very useful, and it is, you know, statistically sound and valid, right? So first, let's, you know, define the bootstrap sample, right? So oftentimes, you know, people denote bootstrap sample as the star, where essentially, you know, each of your bootstrap sample coming from your empirical distribution of the data, right? So this this star from F hat, in other words, you know, it's essentially the I star is one of the original n samples, right, that you have with, you know, equal probability, right? So each of the I star have 1 over n equal probability of being, you know, your original samples. And so immediately, right, you could see that for bootstrap samples, you could have, you know, the 1 star equal to the 2 star, right? You could have, you know, repeated samples. And so how do we use the Z star bootstrap samples, right? Essentially, we want to use the Z stars to estimate the distribution of S of Z. So S of Z here is a very general notation, right, of any statistic, you know, that we derive from the training set, right? So, so to be specific, right, oftentimes, you know, people use bootstrap to estimate the variance a lot. So in terms of the variance, right, in order to estimate the variance, essentially, you know, we think of the variation on your bootstrap sample to be an estimate of the true variation, right? So here the true variation is, you know, the variation of S in general, right? And let's say, you know, we repeat, right? We repeat this bootstrap sample capital B times, so that we have, you know, so this is a capital Z, right? The bold Z, Z star 1, Z star 2, all the way to, you know, Z star capital B, right? So what it mimics is that, you know, instead of having 1 training data set, we would have, you know, capital B training data sets, right? Now all of a sudden we become rich, right? So instead of $1, I have $100. So oftentimes, you know, this B take a large enough value, right? B equal to 100, 200, etc. So instead of this one data set, now I have capital B data sets. So I could estimate the variation of my statistic S, right? Based on this 100 data sets. And that is exactly, you know, what we do here as suggested in the formula, right? So we perform, right? So we perform this S statistic on each of the bootstrap sample, right? And then this S star bar is simply, you know, the bootstrap mean, right? The mean of all of these, you know, capital B bootstrap samples. And this formula, right, is nothing but the definition of your variation, right? So, you know, just to write it, you know, more clearly, maybe, right? We essentially have the S of the star 1, S of the star 2, right? They are all the, you know, repeated statistics that we have, right? We have B of them, and the variation of, you know, these B statistics is used as the estimate for our, you know, original variation of S, right? So that's you know, like the very, you kind of think of this as, like, you could think of this as, you know, like cheating, right? But it's very elegant in the sense that you get 100 data sets, you know, from your original one, right? So so this simple procedure, you know, it may not be 100% accurate, but people try to, you know, further investigate how much bias we might have from this bootstrap procedure, right? So so the bias is, you know, evaluated in terms of the error, right, or the prediction error. So let's see. So similarly, right now, instead of the, so, you know, instead of the S of the star B, we replace it with the F hat, right? So F hat be, you know, the predicted value, but it's essentially, you know, the same F hat applied to different bootstrap samples, right? And so we could get, you know, the bootstrap error that is essentially, you know, taking average for all of your samples and then all of your bootstraps, right? That should be straightforward. But one thing is that, you know, if we directly do this, there's an overlap of training and testing, and that's what we know that, you know, it would cause the bias, right? So instead, we want to, you know, leave out the bootstrap samples that we, you know, we use the XI as the training sample, right? So the idea here is that essentially for XI, right? So XI is sampled, you know, in some bootstrap sample, right? The star, how do we, yeah, so this C is the set, yeah, so essentially it's, you know, this C minus I idea. So let's try to, you know, write this out. So C minus I is set of indices of B that do not contain, right? So if we write this out, is basically all the B, right, that XI, you know, is not sampled, right, from in the bootstrap sample. So with this C minus I definition, essentially, you know, we have that XI is not used in the training. So we eliminate, you know, the overlap, right, of training and the testing. So this error hat 1, it is, you know, a more unbiased estimate, right? So there's some further, you know, improvement for based on this error hat 1, but it's kind of, you know, a little bit minor, and we can skip this part. Let's see, take a example here maybe. So essentially the next example is, you know, what we see as, you know, comparing the bootstrap and maximum likelihood, right? So we know that from the MLE, right? From MLE, we could get, you know, the variance of beta hat, but we want to compare this with, you know, the bootstrap estimate of the variance, right? So that's essentially what we compare. There's some, you know, technical derivation, but the point here is that, you know, if we look at the, so the variance here is indicated by the bound, right? So this bound here. So the MLE bound, we see it's basically, you know, comparable with the bootstrap bound, right? Bootstrap. So, you know, the bootstrap bound, it may be wider in certain area, but, you know, smaller in other areas. And that is because, you know, essentially it would have higher variation when your data has a higher variation, right? So this is, you know, indicated here, right? So at these points, you know, your data itself, right, has higher variation. So the variance estimate from bootstrap is also more variable, right? The same thing here. But, you know, for the data points here, right, they have, you know, less variation in the data itself. So the derived variance is also, you know, more accurate. Yes. Yes, you do get rich, you know, from bootstrap, and that is, you know, rich in the sense of data, right? Okay. So so we do not need to, you know, go into too much detail, but another remark is that, you know, our naive bootstrap, or right, the people, when people use the so-called non-parametric bootstrap, where you simply, you know, directly resample your data, right, Z1 through Zn, it is non-parametric, or, you know, model free. It is a good thing, right, that you do not need to rely on your model assumptions. But as we also see here, right, in some cases, it may have larger variance. So on the other hand, you know, people could do the parametric bootstrap, meaning that, you know, you assume, right, the underlying model, and then instead of bootstrap the X and Y, right, at the same time, you would bootstrap the error term, right? So, you know, instead of bootstrap X and Y or the Z observations, you bootstrap the error term, and that is called parametric bootstrap. So the essentially, you know, parametric bootstrap would be closer to your MLE results, right? Because both, you know, assume like a parametric model, underlying parametric model, right? So the advantage of bootstrap essentially, bootstrap is, you know, most useful when you have complex quantities to estimate, right? If you have some complex statistics you want to, you know, estimate or give variance, you do not have like the parametric formulas, right? Then because of, you know, the non-parametric property of bootstrap, you could perform bootstrap to, you know, estimate those complex quantities. Okay. So a very closely related idea is, so-called bagging. So previously, essentially we use bootstrap like to estimate the variance or, some quantities of interest, right? But could we use, the bootstrap idea to improve the estimate or prediction, right? So here is the bootstrap aggregation idea, or, bagging for short, right? So by aggregation, right? So as we see here, from this formula, aggregation essentially means we take the average, right? So by taking average, we achieve, the goal of, reducing the variance. So that's the main goal of, bagging, the bagging idea. So formally, right, we could write our f hat bag, right? It's, either, so here we can think of this as the prediction, right? So we have the f hat bag prediction on, any of our like external x or future x, target x point, simply as, the average, right, from capital B bootstrap estimates, right? So each one of this f star hat B, right? This is, based on the bootstrap sample D star B, right? For example, we can, write this out as D star 1, D star 2, right? The bootstrap sample that we have. So, so the goal here is like, by taking this averaging, hopefully we want to, reduce the variance. And intuitively, right, we could see that by, simply taking multiple bootstrap samples, we do not change the expectation, or, otherwise the mean does not change, right? So mean, or, the expectation does not change in most cases, right? And at the same time, right, we want to achieve the variance reduction. So unless f hat is a nonlinear or, adaptive function. So so this is especially useful, for high dimensional problems. Why? Because remember, when we have large P, we have increased variance, right? Generally speaking. So for high dimensional problems, by taking this single f hat, right? Taking this, single f hat, we might have large variance, but, through the bagging idea, we would have, reduced the variance. Okay. So below is essentially we do the derivation of, how exactly does bagging achieves variance reduction, but it's, basically some mathematical derivation, right? We could skip this part. And here's the illustration, right? So this illustration actually, comes back to our real life, that so-called wisdom of crowds, right? So the bagging effect is essentially reflected, in this wisdom of crowds, that when we have this consensus, right, from individual opinions, we might achieve, better prediction or better like if you want to make a decision, right, in real life. So the idea is that, the collective knowledge of a diverse and independent body, right, typically exceeds the knowledge of any individual and can be harnessed by voting. So however, right, the key assumption here is, diverse and independent individuals, which may not be the case, in some of the politics in nowadays, right? For example, we might know, you know, like for example, when we have the Republican versus Democrats parties, nowadays maybe within the party, right, the opinions are less and less diverse, right? They are more, you know, clustered with, you know, some same same idea, right? So when your body of people becomes less diverse and not independent, this, you know, wisdom of crowds do not hold anymore. Okay, so as illustrated, you know, from this plot as well, right? We compare, you know, this consensus versus like the individual knowledge, right? So here the experiment is, you know, for each individual to take 10 questions, and we want to, you know, look at the correctness, right, of 10 questions. Yeah, let me finish this example and I'll take a look at the question. So this is, you know, each individual answer 10 questions and we look at the correctness of 10 questions, right? So at the individual level, right? At the individual level, we see that the correctness could, you know, increase linearly, right? Meaning that, you know, for an individual to be more knowledgeable, there's a linear increase in correctness. But at the same time, right, if we take the bagging, right, or, you know, we collect the results for, or, you know, use majority voting, right? We could use, you know, majority voting, get the consensus of, say, you know, 100 individuals. Then we see that, you know, the correctness would increase much faster, right? Using the bagging idea, or, you know, from voting. And also the key here is, you know, say all of your, if you have 100 individuals, right, they should be independent, right? They should not be, you know, correlated. So that's the effect of, you know, bagging, also known as wisdom of the crowds. So let's see the question here. So is the bootstrap sample less than n? Oh, okay, yeah, so maybe that's something, you know, we want to clarify, right? Coming back to the bootstrap sample. So traditionally, right, basically for, let's say, each of the bootstrap sample, first of all, you know, let's clarify, right? So originally, right, you have Z, that is, you know, Z1 through Zn. So n is your sample size, right? Then for each of the bootstrap sample, you know, typically we would also sample the same size, right? So we see that for Z star, it's also, you know, sample size n. So for example here, right, we have n is 100. Now we would repeat, right, this star capital B times. And so there's no restriction, you know, capital B should be less than n. And actually, you know, yeah, so essentially, you know, capital B is not related to n in general. And so basically, you know, you could have B that's much larger than n, right? And B refers to, you know, this Z star 1, right? So for this whole bootstrap data set, right, we want to repeat this procedure so that, you know, we have Z star 1s all the way through Z star B. And, you know, and by convention, you know, we should have probably be at least 100, you know, in most cases. So because, for example, right, you want to calculate the variance from your capital B data sets, right? So you want to have sufficiently large B in practice. Yeah. Yeah, so the bootstrap size must be less than the population size. Yeah, so I want to say, yeah, in, you know, in practice, right, mostly we have, you know, the same bootstrap size as the original size. But yeah, you could have smaller bootstrap size. But that's, you know, yeah, not that common. Yeah, I think in most cases you want to have the same sample size.
No,
yeah.
I think what if I understand it right, what he's saying is that you're taking a sample from the population, and each time, so your bootstrap size obviously has to be the same. So the small n has to be the same for the z's, but
yes,
the bootstrap size should be smaller than the population size. Otherwise, your samples won't have diversity in them, right? Otherwise, each time you're going to get the same big N, right? So the bootstrap size has to be smaller than the population size, the population from which you are
I
drawing
think
samples.
so. Actually, I think the confusion here is, you know, bootstrap is sampling with replacement. What you are saying is, you know, essentially like subsampling, right? Subsampling refers to, you know, sampling without replacement. And actually, you know, that's a distinction we want to clarify. So sampling, you know, with replacement or without replacement. Okay. So for sampling with replacement, that's to be, you know, more specific, right? Let's say we have the samples, you know, 1 through n, right? The samples is just, you know, the sample index, right? 1 through n. For with replacement, we could have, you know, repeated, you know, like the same index, right? 1, 1, 2, 3, you know, or 5, right? You could skip some of them, right? And you could have, you know, repeated samples, say 7, 7. So in this case, right, you do not need your sampling size to be less than n, right? Because you could take, you know, repeated index. But sampling without replacement, that's essentially, you know, subsampling, right? So for subsampling, yes, you do need to essentially have, you know, for subsampling, essentially you need to have like m that is less than n, right? So you only do, you know, like a subsample of your original size, and there's no, you know, replicates, right? So without replacement, there's no replicates. You have to have, you know, m less than n. So to write this out is like you have, you know, your z1 star, z2 star, and to the m star, right? And there's, you know, no replicates here. So your m has to be smaller than n. Does that make sense? Yes.
Yes.
Right.
Thanks a lot. Yeah.
Yeah. Yeah, hope that, you know, answers the question. Yeah, I mean, it is a, you know, distinction we want to make, right? With replacement or without replacement. And typically, you know, when we talk about bootstrap, it is with replacement. Okay. So, and then, so for without replacement, people call this something like sub-bagging or something like this, right? So it's, you know, based on subsampling without replacement. Okay. So yeah, we are almost out of time, but, you know, so essentially, yeah, I will, you know, upload the lecture notes for your reference. And so here's some data example. We, you know, perform, you know, leave one out and k-fold cross-validation. So there's a CV function, right, for you to perform cross-validation. And, you know, we can also perform bootstrap. And let me see. So here's the useful R package, right? It's called the boot R package. And so essentially, you know, you can use the boot function. And here 1000 means, you know, you have b equal to 1000, right? You know, it will give you the So here we see like the T1 star and the T2 star, they are the bootstrap estimates, right? So bias means, you know, your estimates, right? They are very close to the original. Right? Your bootstrap estimates, they are very close to your original estimates. But in addition, right, you get the bootstrap standard error. You get the bootstrap standard error. So yeah, so unfortunately, you know, we may not go into the high dimensional inference part, but let's see, I want to, you know, at least introduce the, so once again, right, so the high dimensional inference is, you know, when we have P greater than N, and, you know, we want to identify, however, you know, the sparse regression model, right, essentially identify, you know, the important predictors out of, you know, all of the P predictors. And we want, you know, the unbiased coefficient estimates, right? And in addition to the unbiased coefficient estimates, we want the variance estimates as well. So, so compared to, you know, like the lasso or the variable selection, essentially lasso does not provide variance estimate, right? So there's no, you know, inference or the variance estimate for lasso. So that's the key advancement when we consider high dimensional inference. There are, you know, some previous works. If you are interested, you know, you should refer to these papers to, you know, get a sense. And, you know, actually from previously, like William's question, you know, these deep biased estimators, they exactly, you know, they want to estimate this X transpose inverse, so-called, you know, precision matrix. And there are some, you know, other methods as well. And I wanted to, you know, introduce like some methods that we developed, you know, by our own, and in order for us to do this inference. But maybe the idea here is that, you know, we use the resampling idea, right? There's more details to follow, but essentially, you know, we use the resampling idea and try to estimate our beta hat, you know, and for it to be, you know, unbiased in the high dimensional case, okay? And we also, you know, derive the statistical inference in the sense, right, we derive the variance estimate. Let's see here. Wait, yeah, anyways, so we get, you know, this variance estimate, right, for beta. So at the end, you know, we get beta j hat, say for example, right, plus minus this vj hat. So that is, you know, the confidence interval, or, you know, how we could do statistical inference in the high dimensional case. Okay. Yeah, so we also developed some R package, and there's, you know, more numerical studies to show the performance. Yeah, anyways, I hope, you know, the materials we do cover, it, you know, gives you some useful information, and I will stop here.
Yeah, so thank you again, Dr. Fay, for very informative presentation on statistical learning. At this point, anyone has any questions or comments for Dr. Fay? You can speak it out, or you can type it in the chat area.
Yeah, I think this is a great session. So thanks a lot. It's a lot of materials, but we'll go back and reread it and watch the videos. But really very informative. Thanks so much.
Yeah, thank you. Yeah, you know, I'm glad it's, you know, informative and helpful to you.
Any other questions? I know it's 2 p.m. Everybody wants to leave. Any last question, comments? Otherwise, thank you so much, all of you, for coming, and thank you, Dr. Faye, for this presentation. So we are going to meet again next week to continue with this discussion. Sure. Dr. Faye will again be the instructor next week. So we'll see you all next week, same time. Have a great weekend.
Yeah. Thanks all. Yeah, see you next week.
Yeah, thank you. And there's going to be a TA session as usual on Saturdays. We have it from 5 to 7. So 5 Eastern to 7 p.m. And hopefully the materials will be updated. There will be the video link on the general channel. So keep an eye on that. Okay, thank you.
Okay. All right, thanks. Bye, everyone.
All right, bye-bye.